The Open Systems Interconnection, OSI, and Transmission Control Protocol, Internet Protocol, TCP/IP networking models are both crucial frameworks for comprehending networks. In our session today, we delve into the layers and functionalities of each model, gaining insights into how data flows from source to destination. Additionally, we dedicate time to exploring the Transmission Control Protocol, TCP, and the User Datagram Protocol, UDP. Finally, we conclude the video by examining the devices employed in contemporary networks, the media employed to connect these devices, and the various types of network topologies. Layered models provide a valuable framework for comprehending networking concepts and technologies, enabling us to understand the process of communication across a network. Two prominent models, namely the TCP/IP and OSI models, play a significant role in facilitating interoperability among various vendor product lines. While the OSI model primarily serves as a tool for explaining networking concepts and aiding in troubleshooting, it is the protocols within the TCP/IP suite that govern the operation of modern networks. Therefore, it is essential to possess a strong understanding of both models, including their respective layers and how they align with each other. For a visual overview of the two models, to avoid confusion when discussing networking models, it's helpful to follow these straightforward guidelines. When referring to the layers of a model, we typically mean the OSI model. When discussing protocols, we generally refer to the TCP/IP model. In the following sections, we will provide a brief overview of the OSI layers and the TCP/IP protocols. This table summarizes the layers of the OSI model and provides a brief functional description. The following mnemonic phrase, in which the first letter represents the layer, A stands for application, can help in memorizing the name and order of the layers from top to bottom. All people seem to need data processing. The TCP/IP model provides a comprehensive structure comprising 4 distinct layers, each serving specific functions critical for effective communication. This model serves as a universal standard, promoting interoperability across different systems and networks. This table summarizes the layers, their respective functions, and the commonly employed protocols associated with each layer. By following this model, network administrators and developers can ensure seamless communication and data exchange within TCP/IP networks. By adhering to the TCP/IP model and leveraging the appropriate protocols at each layer, network systems can communicate effectively and efficiently. This standardized approach ensures compatibility and enables seamless communication across different platforms, devices, and networks. In the upcoming days, we will delve into a more detailed review of these essential TCP/IP protocols. For now, here's a concise description of the main protocols. 1. Domain Name System, DNS, maps domain names to their corresponding IP addresses, enabling hosts to connect to websites or services. 2. Telnet allows administrators to remotely log in to a host or network device for configuration and management purposes. 3. Simple Mail Transfer Protocol, SMTP, Post Office Protocol, POP3, and Internet Message Access Protocol, IMAP. These protocols facilitate the exchange of email messages between clients and mail servers. 4. Dynamic Host Configuration Protocol, DHCP, automatically assigns IP addresses and network configuration parameters to clients upon request, streamlining network management. 5. Hypertext Transfer Protocol, HTTP, enables the transfer of information between web clients and servers, forming the foundation of the World Wide Web. 6. File Transfer Protocol, FTP, facilitates the transfer of files between an FTP client and server, allowing efficient uploading and downloading of data. 7. Simple Network Management Protocol, SNMP, permits network management systems to monitor and manage network devices by collecting and organizing information about them. 8. Transmission Control Protocol, TCP, establishes reliable, connection-oriented communication channels between hosts, ensuring the secure and ordered delivery of data. 9. User Datagram Protocol, UDP, provides fast, connectionless communication suitable for lightweight or time-sensitive data that can tolerate some loss or duplication. 10. Internet Protocol, IP, offers a unique global address to computers for communication over the Internet, routing data packets across networks. 11. Address Resolution Protocol, ARP, resolves IP addresses to their corresponding hardware addresses, MAC addresses on local networks. 12. Internet Control Message Protocol, ICMP, sends error and control messages, including host reachability and service availability notifications. 13. Ethernet, a widely used LAN standard responsible for framing and transmitting data packets across the local network. 14. Wireless, encompasses IEEE 802.11 standards for wireless local area networks, WLANs, and cellular access options, enabling wireless connectivity for devices. Understanding these protocols is crucial for comprehending the functioning of the TCP/IP model and ensuring efficient and secure communication within networks. Understanding how data is transmitted across networks involves the concept of protocol data units, PDUs, and encapsulation. As data travels through the protocol stack, different protocols add relevant information at each layer, enhancing the encapsulation process. At each layer, the data takes the form of a PDU. To provide a clearer picture, let's explore the PDUs at each layer of the OSI model, as presented here. Now, let's delve into the steps involved in the communication process, which allows data to flow from a source to a destination. Step 1. At the originating source device, data is created at the application layer, tailored to the specific requirements of the application. Step 2. As the data progresses down the protocol stack within the source device, it undergoes segmentation and encapsulation. Each layer adds its respective header or encapsulation information, preparing the data for transmission. Step 3. At the network access layer, the encapsulated data is placed onto the network media, ready to embark on its journey across the network. Step 4. The data traverses the internetwork, encompassing various network media and potentially passing through intermediary devices such as routers or switches. Step 5. Upon reaching the destination device, the data arrives at the network access layer, where it is received. Step 6. As the data ascends the protocol stack within the destination device, it undergoes a process of decapsulation. Each layer strips off the relevant headers or encapsulation information applied during the transmission, gradually revealing the original data structure. Step 7. Finally, the data is delivered to the destination application at the application layer of the destination device, where it can be processed and utilized accordingly. By following these steps, data is efficiently transmitted from any source to any destination, facilitated by the encapsulation and decapsulation processes occurring throughout the protocol stack. The application layer, which is part of the TCP/IP model, plays a crucial role in enabling communication between software applications, such as web browsers, and the underlying network infrastructure. It serves as an interface that facilitates the exchange of information. Let's take a closer look at how the process of requesting and receiving a web page typically unfolds. Step 1. When a user initiates a request to access a web page, their web browser generates an HTTP request. This request includes an instruction to get a specific file, often representing the website's homepage. The HTTP request is then sent over the network. Step 2. The web server receives the HTTP request and processes it. It generates an HTTP response, which contains the requested file or relevant information. In the header of the HTTP response, a status code is included. The status code, such as 200, indicating a successful request with returned information, or 404, indicating that the page was not found, provides important information about the response. Both the HTTP request and the HTTP response are encapsulated within headers. These headers contain vital information that allows the application layers on each end device to communicate effectively. It's worth noting that regardless of the specific application layer protocol being used, whether it's HTTP, FTP, DNS, etc., the process of communication between the application layers on the end devices follows a similar pattern, ensuring seamless interaction. By employing this standardized approach, the application layer facilitates smooth communication between software applications and the underlying network, enabling the retrieval and delivery of web pages and other resources. The transport layer, through TCP, provides a mechanism to guarantee delivery of data across the network. TCP supports error recovery to the application layer through the use of basic acknowledgement logic. Adding to the process for requesting a web page, TCP operation works like this. Step 1. The web client sends an HTTP request for a specific web server down to the transport layer. Step 2. TCP encapsulates the HTTP request with a TCP header and includes the destination port number for HTTP. Step 3. Lower layers process and send the request to the web server. Step 4. The web server receives HTTP requests and sends a TCP acknowledgement back to the requesting web client. Step 5. The web server sends the HTTP response down to the transport layer. Step 6. TCP encapsulates the HTTP data with a TCP header. Step 7. Lower layers process and send the response to the requesting web client. Step 8. The requesting web client sends an acknowledgement back to the web server. If data is lost at any point during this process, TCP must recover the data. HTTP at the application layer does not get involved in error recovery. In addition to providing TCP, the transport layer provides UDP, a connectionless, unreliable protocol for sending data that does not require or need error recovery. This table lists the main features that the transport protocols support. Both TCP and UDP support the first function. Only TCP supports the rest. TCP, the Transmission Control Protocol, holds a touch when it comes to ensuring reliable data transmission. It takes on the responsibility of error recovery, but to achieve this, it sacrifices a bit of bandwidth and engages in additional processing cycles compared to its counterpart, UDP. Both TCP and UDP depend on IP for end-to-end delivery, with TCP focusing on catering to the needs of applications residing on sending and receiving computers. To fulfill its mission, TCP utilizes a diverse range of fields embedded within its header, each playing a crucial role in providing the desired services. Port numbers play an essential role in both TCP and UDP. These numbers are the first two fields in the TCP header, also present in the UDP header. They enable TCP and UDP to multiplex multiple applications on a single computer, much like having multiple tabs or pages open in a web browser. When you open a new tab and request a web page, TCP assigns a unique source port number, sometimes multiple, while usually assigning destination port 80 for all sessions. Let's say you have 5 web pages open. TCP ensures that each page has a different source port number, while the destination port remains consistent. This clever multiplexing allows the web browser to display the data in the respective tabs accurately. TCP and UDP dynamically assign source ports, typically ranging from 1024 to a maximum of 65535. Port numbers below 1024 are reserved for well-known applications. This table provides a list of popular applications and their corresponding well-known port numbers, ensuring seamless communication across the network. TCP, the Transmission Control Protocol, takes on the responsibility of ensuring reliable data transfer between two connected devices by providing error recovery, also known as reliability. This is achieved through the use of the sequence and acknowledgement fields in the TCP header. During a data transfer session, TCP tracks every byte of data being transmitted and received. The sequence field indicates the sequence number of each byte sent, while the acknowledgement field specifies the next expected byte to be received. In a normal scenario, as shown in the left figure, the web client sends an acknowledgement with the value 4000, indicating that it has successfully received all data up to that byte. This is known as positive acknowledgement. However, in the figure on the right, an error occurs, and the second TCP segment is lost during transmission. As a result, when the web client sends an acknowledgement, it sets the ACK field to 2000. This is called positive acknowledgement with retransmission, PR, because the web client requests the retransmission of the missing data. In response to the PR, the web server resends the data starting from segment 2000, allowing for the recovery of the lost information. To ensure further reliability, the web server sets a retransmission timer and awaits acknowledgement. If the acknowledgement is lost or all transmitted segments are lost, the timer expires and the web server resends all segments. Through this error recovery process, TCP ensures that missing or lost data is retransmitted, maintaining the integrity and reliability of the data transfer session. TCP incorporates flow control using a mechanism called windowing. Flow control allows the two communicating devices to manage the amount of data being sent to ensure efficient and reliable transmission. When establishing a TCP connection, the two end devices negotiate the initial window size. This window size represents the maximum amount of data that the sender can transmit before receiving an acknowledgement from the receiver. This negotiation ensures that the sender doesn't overwhelm the receiver with more data than it can handle at once. During the lifespan of the connection, the window size can be dynamically adjusted based on the network conditions and the capacity of the receiving device. The devices may incrementally increase the window size to optimize data transmission until it reaches the maximum limit of 65,535 bytes. However, if errors or congestion occur, the window size may be reduced to avoid data loss or network congestion. The window size value is specified in the window field of the TCP header. It represents the number of bytes that the receiver is currently able to accept and process. Once the sender has transmitted data equal to the window size, it must wait for an acknowledgement from the receiver before sending the next window size of data. This ensures that the sender doesn't overwhelm the receiver's buffer and allows for a controlled and synchronized data transfer process. By implementing flow control through windowing, TCP optimizes data transmission by adapting to the capabilities and conditions of the receiving device, ensuring reliable delivery and preventing congestion or data loss. During connection establishment, the involved parties initialize sequence and acknowledgement fields, agree on port numbers, and determine the window size. The three-way handshake, illustrated in the figure on the left, is necessary before data transfer can commence. In the figure, D port and sport represent the destination and source ports, while SEQ denotes the sequence number. The SIN and ACK flags in the TCP header play a vital role in signaling connection establishment. TCP sets the sequence number and acknowledgement number fields to suitable values that fit within the 4-byte fields. The initial sequence number is a randomly generated 32-bit number unique to each new transmission. The acknowledgement number is received in response and increments the sender's sequence number by 1. Upon completion of data transfer, a 4-way termination sequence takes place. This sequence employs an additional flag known as the FIN bit, as shown on the right. The FIN bit indicates the intention to terminate the connection and initiate the closure process. TCP and UDP are both transport layer protocols in the TCP/IP suite, but they differ in their approach to establishing and terminating connections and the level of services they provide. TCP is a connection-oriented protocol, which means it establishes a reliable, ordered and acknowledged connection between endpoints before data transfer begins. It ensures that data is delivered accurately and in the correct order. TCP also incorporates features like windowing for flow control and reordering of data packets if necessary. It provides a high level of reliability, but incurs additional overhead and processing. On the other hand, UDP is a connectionless protocol, meaning it does not establish or terminate connections before transmitting data. It does not guarantee reliability, windowing, or reordering of data. UDP focuses on providing a lightweight and fast data transfer mechanism. It offers data transfer and multiplexing using port numbers, allowing multiple applications to use the same network connection simultaneously. UDP has lower overhead and processing requirements compared to TCP, making it suitable for applications that prioritize low latency and real-time communication over guaranteed delivery. Applications such as Voice over IP, VoIP, often utilize UDP. VoIP services trade off the possibility of some data loss for reduced delay and real-time communication. In scenarios where minimal delay is crucial, the occasional loss of some data is acceptable. UDP enables faster communication by eliminating the need for establishing and maintaining a connection, resulting in lower latency. This figure provides a comparison of the headers used in TCP and UDP, illustrating the structural differences between the two protocols. The Internet layer of the TCP/IP model, powered by the Internet Protocol, IP, plays a crucial role in providing unique addresses to host computers. Each computer on the network is assigned a distinct IP address, allowing for proper identification and communication. Furthermore, the Internet layer encompasses the process of routing, enabling routers to determine the most efficient path for transmitting packets to their destinations. Continuing with the web page example, the IP layer comes into play as the data progresses from the transport layer. 1. The web client initiates an HTTP request. 2. TCP encapsulates the HTTP request, preparing it for transmission. 3. IP encapsulates the transport segment into a packet, assigning source and destination addresses to it. 4. The lower layers process and forward the request to the web server. 5. The web server receives the HTTP request and responds with a TCP acknowledgement to the requesting web client. 6. The web server sends the HTTP response back to the transport layer. 7. TCP encapsulates the HTTP data, preparing it for transmission. 8. IP encapsulates the transport segment into a packet, assigning appropriate source and destination addresses. 9. The lower layers process and transmit the response to the requesting web client. 10. The requesting web client sends an acknowledgement back to the web server, acknowledging the successful receipt of the response. In addition to addressing, the IP layer also encompasses the crucial task of routing data from its source to the intended destination. The process of routing ensures that packets traverse the network efficiently, following the best possible path. The operation of IP, including addressing and routing, will be further explored and discussed in the upcoming days. The Internet layer, with its IP protocol, forms the backbone of communication in the TCP/IP model, enabling proper addressing, routing, and seamless data transmission across the network. The TCP/IP network access layer is responsible for the physical delivery of IP packets across a network. It defines the protocols and hardware necessary to establish a connection between networked devices and the physical media over which data is transmitted. The network access layer encompasses various protocols tailored to different types of media through which data travels. For instance, data may traverse multiple media types, such as Ethernet, point-to-point, PPP, frame relay, and multi-protocol label switching, MPLS, before reaching its destination. At each transition from one media type to another, the network access layer provides the protocols, cabling standards, headers and trailers required to successfully transmit data across the physical network. In certain scenarios, a local link address is essential to facilitate data transfer from one hop to the next. For example, within an Ethernet LAN, media access control, MAC addresses, are employed between the sending device and its local gateway router. At the gateway router, the Ethernet header may be replaced with an MPLS label, serving the same purpose as MAC addresses in Ethernet, which is to guide the data across the link from one hop to the next. Some protocols, such as PPP, do not necessitate a link address, since only a single device on the link can receive the data. With the understanding of the network access layer, let's simplify and summarize the process of requesting and sending a web page. 1. The web client sends an HTTP request. 2. TCP encapsulates the HTTP request. 3. IP encapsulates the transport segment into a packet, adding source and destination addresses. 4. The network access layer encapsulates the packet into a frame, addressing it for the local link. 5. The network access layer transmits the frame as bits on the media. 6. Intermediary devices process the bits at the network access and internet layers and forward the data toward the destination. 7. The web server receives the bits on the physical interface and moves them up through the network access and internet layers. 8. The web server sends a TCP acknowledgement back to the requesting web client. 9. The web server sends the HTTP response down to the transport layer. 10. TCP encapsulates the HTTP data. 11. IP encapsulates the transport segment into a packet, adding source and destination addresses. 12. The network access layer encapsulates the packet into a frame, addressing it for the local link. 13. The network access layer transmits the frame as bits on the media. 14. Lower layers process and send the response to the requesting web client. 15. The response travels back to the source over multiple data links. 16. The requesting web client receives the response on the physical interface and moves the data up through the network access and internet layers. 17. The requesting web client sends a TCP acknowledgement back to the web server. 18. The web page is displayed in the web client's browser. In this process, the network access layer plays a crucial role in encapsulating data into frames, addressing them for the local link, transmitting the frames as bits, and handling the physical delivery of data across the network. In the TCP/IP model, each layer adds its own header information as data travels down through the layers. This process is known as encapsulation, where a new header is added at each layer. Additionally, at the network access layer, a trailer is also appended. The encapsulation process can be understood through the following 5 steps. Step 1. Application layer encapsulation. The application layer adds any necessary headers to the application data. For example, in the case of an HTTP response, An HTTP header is added, followed by a portion of the web page content. Step 2. Transport layer encapsulation. The transport layer encapsulates the data provided by the application layer within a transport layer header. TCP or UDP headers are commonly used for end-user applications. Step 3. Internet layer encapsulation. The Internet layer, IP, encapsulates the data from the transport layer within an IP header. In the TCP/IP model, IP is the protocol used at the Internet layer. Step 4. Network access layer encapsulation. The network access layer encapsulates the data from the Internet layer within a network access layer header and trailer. It is the only layer that uses both a header and a trailer. Step 5. Transmission. The bits representing the encapsulated data are transmitted over the physical medium. The physical layer encodes the data into signals and transmits the frame. This figure visually represents the encapsulation process, with numbers corresponding to the 5 steps mentioned above. We hope this video helped you on your journey towards becoming a cybersecurity expert. Remember to subscribe to our channel and turn on notifications so you never miss out on our latest content. And if you found our videos helpful, please give us a thumbs up and share them with your friends and colleagues. Don't forget to check out the links and description for our Anki flashcards and to donate to St. Jude Children's Research Hospital. Your support can make a real difference in the lives of those in need. Thanks again for watching, and we'll see you in the next video.